well, Chris is like, I turned it in. I'm good now. Welcome back from the crazy 4-day weekend, right? I hope that you had a good 4-day weekend. I hope that it was all that you needed it to be, whatever that is. I don't know. A couple of little logistical things, and then we'll jump in and do some physics today. First of all, it totally snuck up on me. It may have snuck up on you as well. Did you know that tomorrow is parent-teacher conferences? What? I didn't know that either. Let your parents know. I'll bring candy. You guys come and we'll have some conversations about physics. Sound good? It'll be great. 4:15 to 7:45 tomorrow in the Commons. It'll be fun. Come with us. Before I talk about plans for this week, I want to introduce you to a new guest that we have with us. I'm going to let you introduce yourself, and does that sound good? They can all turn that way. There you go. Yeah.
I'm an undergrad in physics at the University of Iowa. I'm doing my master's in education, also at the University of Iowa. I was at MC, spent 10 years with my wife and 2 rabbits. So they're lion-headed rabbits, if anybody knows breeds. Yeah. So anyway, I'm excited for this opportunity to be with you guys. I've been with you until about May or so. And,
like we're gonna have a big party. It's called the AP exam, and you'll be here like right until it. It'll be great. Yeah, yeah. A party. Yeah, I mean, what other kind of party is there, Bo? Let's go. Anyway, all right. So, what was I gonna say? I don't know. I had something else in my brain, but it's gone now. But we are glad that you're here. So thank you so much. And he'll be here every day, and it'll be great. There might be some like bouncing between Mrs. Murphy's class and mine, but he'll be here most days and teach you some physics too, because why not, right? It's a good time. So you all got an email from me on Friday morning, right? Said, yay, sorry I can't see you. But I don't know if you caught the whole thing about how there was actually a snow day on this very like lesson day last year, which is fortuitous and worked out, I guess, for me, because I didn't have to make a new video. If you haven't watched the Standing Waves video, you probably should do that, my friends. Today, we are going to review some concepts. I've got a demo for you. We're going to go through some things. Wednesday is going to be the day that we do our analysis of the Standing Waves lab. That was the lab that you did on Thursday. We were going to do that today, but I didn't feel like we were quite ready for it. So if you have not taken all of your data from that Standing Waves lab, then maybe come visit me during Liberty Time so you can finish that up, okay? Just to make sure you've got it all. So you can do your analysis, and then I've got some workbook pages for you to work on that day. Thursday, we're gonna do another lab. This is my favorite of all of the labs that we do in this unit, is this one here. We'll write an analysis and conclusion for it on Friday. Monday will be a review day, and next Tuesday will be Unit 6 test, okay? Questions, issues, or concerns about any of that before we move on and get ready to go? Okay. We're going to warm up today. We'll do a demo and then some other things. But in case I forget to tell you, I think we'll have time at the end, but you know how that goes for me. Your homework for tonight, I did assign you the first set of multiple choice questions from the AP Classroom. This is that thing online where you have like the multiple choice questions that may or may not tell you the right answers. Remember, you log in and do all of that stuff. So we'll try and get that done at the end of class today, but in case we don't, put that on your list of things to do for tonight. All right, we're gonna hop in and do this warm-up problem. So this is a ranking task. It's a ranking task that is easier to do if you understand standing waves, but even if you don't, you can totally approach it. I'm gonna read it because it's kind of small up there. Actually, maybe it's a little bit bigger here too. Oh, nope. There we go. All right. A string is stretched so that it's under tension, so that means it's tight, and held at both ends so the endpoints don't move. A mechanical oscillator then vibrates the string so the standing wave is created. So if you turn your heads to the side, this is exactly what we did on Thursday, okay? The dark line in each diagram represents a snapshot of the string at an instant in time when the amplitude of the standing wave is at its maximum. The lighter lines represent the string at other times during a complete cycle. All of the strings are identical except for their lengths, and all of the strings have the same tension. The number of nodes and antinodes in each standing wave is different. The lengths of the strings and the amplitudes are given in each figure. Okay, so there's a lot of information there, but you can kind of parse it out. So there are your 4 pictures, and then it asks you to rank the frequencies of the waves. I'm going to give you 2 minutes of quiet to work on it by yourself, maybe one. We'll see how you're doing, okay? And then I'll let you discuss. Sound good? So everybody for themselves here for just a moment. Think about this. See if you can figure out how to approach the problem. Okay. I'm not saying you have to have an answer yet, but let's just check in. I don't need an answer. It's okay. So can you tell me so far what you know? No, nothing. I'm done. What'd you say? Okay, you know the lengths and the amplitudes. Awesome. That's good stuff to know. Let's write that down. We know the lengths. We know the amplitudes. Okay. What are you trying to find? Frequencies. Okay. All right. Now what? Do you have an equation that involves waves that includes the frequency? Like a simple one? What is it? F equals what? V over 2L. Yeah, you could, yeah. Sorry, that was not the equation I expected you to say. Okay. And so we were just talking about this. A teaching moment for us here real quick was sometimes when you ask a question, you expect students to say a certain thing and you're like, you know exactly the response to give. That's not the word, but it works. And so we're going to go with it. Awesome. Where did you get this from? From the video, because you said it on the video. Yes, what's F here? Frequency, the fundamental frequency, right? Yeah, the frequency of a fundamental, right? And then you've got V, and then you've got 2 times the length. Yeah, that's true. That's true. But this is only for the fundamental standing wave. Are any of those fundamental standing waves? Do you guys understand what I mean by that question? Well, okay, thank you for being honest. I appreciate that. Can somebody tell me what the fundamental standing wave would look like for a string like this? Can you put words to that? Ira? It was good. Yeah. So it's got 2 nodes, one at each end, and then an antinode in the middle. Why is that? Because that's the simplest standing wave. So if you take your slinky out into the hallway, right, and you want to get the simplest standing wave, the lowest frequency standing wave, that's what you would look for, and then you figure out the frequency there. Okay. If you increase the frequency, then you can get something more complicated, like having a node in the middle, or 2, or 3, or 4, or 7, or whatever. Right. But that's the simplest one. Yeah. Do you remember where this came from? Much harder. There's a very simple equation for a wave. Yeah. Yeah. Does that make sense? So this thing here, the one that you said, Eden, is right. That's totally true. But again, this is just for the fundamental wave, whereas this is like the very basic thing where and the difference here is that we got lambda as opposed to L. Does that make sense? Because when we figured out the wavelength of this thing, it was twice the length of the standing of the string. This is the one I would look at. Can you find the wavelength of this wave? Morgan, you made a really good noise. Can you tell me why you made that noise? I'm not trying to put you on the spot, and you can say no if you want. That's fine. If I start here, okay, oops, come on, thing. Tell me when to stop. Okay. Does everybody agree that that's a wavelength? Okay. If I know that the string is 28 centimeters long, can I then figure out the wavelength? Okay. So I'm not asking you to do it yet, but could you figure out the wavelength of each of these? Okay. So that means we know that, and we not only know the length, but now we can figure out the wavelength. So I'm going to add that to the list of things that we know. We want to know the frequency. So we know the wavelength. We want to know the frequency. What else do we need to know? What's the other thing in the equation? Velocity. What dictates the velocity of a wave on a string? I didn't explicitly say this in the video, I don't think. I can't remember for sure. Does anybody know how you change the speed of a wave on a string? It's the tension. Yeah. How many of you play or have played a stringed instrument before? Anybody? How many of you, when you were learning how to play a stringed instrument, played a stringed instrument out of tune ever? Yeah, never, like, never did that, never did that. I've never done it, but I understand that it's a thing and it can sound really bad, right? When it's out of tune, that basically means that the sound is not traveling on that string at the right speed. So we need to change the tension. Changing the tension and changing the type of string changes the speed of the wave on the string. Okay, so let me write that down again. This would be a good thing to write down if you haven't written it down yet before. So I'm just, heads up, right? We learn while we do. So here we go. Just a piece of information. The speed of a wave on a string depends on the tension of the string and also the type of string. Right? Again, I've not played any musical instruments, but I understand that if you're going to string a guitar or a violin or whatever, the string that you use on one end is not the same, like on one side is not the same as you on the other side, right? Like one of them's a lot thicker than the other. Is that true? You're shaking your head like, yeah, like you can speak with authority more than I can. Yes, she's like, yes, it's true, right? So part of that is because the speed of a wave on a string depends on the type of string. So you have like an E string or a G string or something like that. True? Again, I'm making these things up because I don't know, but that's what my understanding is. So the type of string and the tension of the string are what dictate the speed of the wave on the string. Okay? I'm going to give you another 2 minutes. I want an answer on your board. Okay? Go, go, go. You now have everything you need, I think. All right. Show me your boards. Got lots of things here. C, B, A, B. I know. I did that on purpose. Doesn't happen usually, but today it did actually. That's on Chris. Is there a reason? All right, let's talk. Oh yeah, it is just opposite, isn't it? So talk to me. I have C, D, A, B, and I have B, A, D, C. They are just flips of each other. So they're in the same order, but why should C be the greatest frequency or should B be the greatest frequency? Convince me. If you wrote it down, that means you know it. I think at least somebody at your table. No. Oh. Hold on. Fn equals, what'd you say? Said she's stealing your thunder here. Okay. Okay. You did n divided by L, essentially. Did she steal what you were gonna say? Jeez. Do you guys agree with her? Does that make sense? So this is the way that Eden wanted to do it too. And I was like, no, 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 do it the other way. It's easier. Sorry about that. F1 equals n times 0 with 2 L, the v and the 2 are gonna be the same. So n divided by L. Did anybody do it the way that I suggested before with the lambda v and s? Or no? You're like, yeah. Okay, that's okay. That's the way I did it too. So high five. Yay for us. So you found lambda by essentially counting the number of antinodes, right? I mean, like that's essentially what you're doing, dividing to find the wavelength. Yeah, yeah. Now you guys got it. It was just backwards. Was that just like an inversion thing? Do you think?
Yeah.
Okay. Does it make sense? Okay. Okay. How are we doing, team? We good? Sweet. All right. Yes, not yesterday. A few days ago, we measured the speed of sound. Do you remember that? We snapped our fingers and measured the speed of sound. It sounds like a magic trick, but really it wasn't. It was really cool, right? We set the sound down and came back and we did it. It was great. Today we're going to measure the speed of light. Okay? That's my plan for the day. The reason that we're going to measure the speed of light today is because we don't get to do a light unit, so we have to do it today because it has to do with standing waves. So I want you to we're just going to write down a couple notes because it's exciting. Anybody know how fast light travels? No, much, much faster. Let me tell you. That's a lot. 1, 2, 3, 4, 5, 6. 300 billion meters per second. Did I do that right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's right. Yeah. That's fast. I don't like to write zeros usually. I like to write that out so you see how big it is. That's a lot, right? So being really, really clear, 300 billion of this in 1 second. What's that? No, million, sorry, 300 million. I said that backwards, sorry, thank you. 300 million of this. I mean, at that point, like, but it does matter, doesn't it? 300 million of one of these in every second. So it does take time, but it doesn't take a lot of time for speed to travel. So 3 times 10 to the 8th meters every second. That's in a vacuum. Remember we said that most waves can't travel in a vacuum, but light can, and our proof for that is what? Stars, the sun, we're alive, right? All of these things. If it didn't work, we wouldn't be able to. So it moves at 3 times 10 to the 8th meters per second in a vacuum. Through air, it moves just a little bit slower, but not appreciably, like enough to matter. So it's 2 times 10 to the 8th meters per second. That's cool. Did you guys know that there are lots of different kinds of light? Yes? What kinds of light are there? There's like this whole spectrum. Can you tell me some of them, Chris? What's some light that you know about? Visible! Why is it your favorite? Oh, okay. What else you got? Other kinds of light. Tell me what you got. Yeah. Ultraviolet, for sure. Ultraviolet light also moves at 3 times 10 to the 8th meters per second. But can you see it? No. Are the wavelengths smaller or bigger? Do you know? Wavelengths are a little bit smaller. The frequency is a little bit bigger. Yeah. What else you got? Are you pointing up there? You can totally just read something off of there, can't you? Go for it. Tell us one. Infrared. Absolutely. What else you got? Somebody else. Ira, what do you see up there? X-rays. Now I'm not writing these in good order anymore, so don't like judge. Like that's not how you talk to me. What else you got? What else you got? Radio waves. Maybe I'll keep going that way. So here's a weird thing, friends. Radio waves are light waves. Radio waves are not sound waves. A lot of people want to say radio sound because you hear it, right? Turn your radio, but really it's a light wave that's going through, and then your radio or whatever converts it to a sound wave to get to your ears. What else you got? There's at least one more that I need. Oh, that wasn't it, but good guess. There it is. Who said that? Yeah, that's the one I really wanted. Why do I want the microwave? Because we're going to study the speed of light of a microwave wave. Okay? Why? Because we have a microwave. How do microwaves work? Do you know? No. How do microwaves work? Well, let me back up. What is a microwave used for? Why do you have microwaves at your house? To heat things, right? So this is like one of these beautiful conversations that's going to put so many good physics things together, so I need you with me here, okay? So how do microwaves work? Do they send heat into the chamber? They do not. No. How do they work? Does anybody know? They are. Do you know why they're good at heating water? This is so cool, you guys. So you remember 2 snow days ago, you watched that video on resonance. You remember this? And you're like, oh, resonance theory, I don't understand it at all. You remember you saw the little kid that was being pushed on the swing? Yeah? And when you push that kid on the swing, if you push at the right frequency, then the amplitude gets what of the kid on the swing? Bigger. Does that make sense? And then you saw the little kid that could pump their legs, and so they were applying a force at the right frequency so that the amplitude would get bigger and bigger and bigger. Yeah? Okay? So if you apply a force at the right frequency, you can get things to vibrate at bigger and bigger and bigger and bigger amplitudes. Okay? Most food has a lot of water in it. Water molecules, just like a pendulum, just like a wine glass, just like a whatever, has a natural frequency. if you push the water molecules at that natural frequency, they're going to oscillate, and their oscillation is going to get bigger and bigger and bigger and bigger. And you all know from chemistry, we did this chemistry and thermo, right? If something moves around a lot more, what's going to happen to its temperature? It's going to go up. So literally, the microwaves, like the appliance, sends microwaves, the wave, into that little chamber, okay? And those waves push, 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 push onto the water molecules. They get bigger and bigger and bigger and bigger and bigger, and then they cause whatever, the soup or the, TV dinner or whatever it is to heat up. Does that make sense? That's what's going on. It's really pretty straightforward. So resonance, we got it, okay? The other thing that's really cool about microwaves is that the size of the chamber is very specific, right? Because in a microwave, the appliance, we establish standing waves of microwaves, the wave, okay? So that you can get lots and lots of resonance points. So when I was a kid, way back in the day, right, there was a feature about microwaves that did not exist. And it was a feature that caused me to have to take my soup out when I was warming it up and stir it around and then put it back in prior to finishing up the heat. Do you know what I was missing in my microwave that was super old? The spin, the turntable, right? So most microwaves that have been manufactured in the last 20 years have a turntable in them, don't they? Yeah, yeah. Why do they have a turntable? So you don't have to stir your soup as globally. Of course, duh. Why would I have to stir my soup? Has anybody ever experienced a microwave without a turntable before? What happens? It's unevenly heated, right? There are hot spots and there are cold spots. And so like if you're trying to like heat up some soup, then you got some spaces where it's got like really, really hot and then other places that like hasn't been heated up at all. Let's think about what's going on there. So I said that inside that microwave chamber, there was a standing wave. And so you've got a standing wave. I'm just pretending it's this one here, okay? And without the turntable, that standing wave has got places that are hot spots and cold spots. What would that correspond to on something like this? What do you think? If I put my bowl of soup, whoa, we'll pretend it's tomato soup. Oh, it's pink. I meant to have orange. There we go. There, we'll put orange soup in there. Right? Is there any wiggling that's going on for the tomato soup that's sitting right there? No. What's going to happen at that spot? Is it going to get heated up? No. But right here, it's going to be hot. Does that make sense? Okay. So we got standing waves inside a microwave, and if you have that turntable, then it moves around so you don't have as many hot and cold spots that are only stuck in one place. But if you take the turntable out, which is what we're going to do today, then we can see it. So I'm going to meet you back by the microwave, and we'll go microwave some gummy bears. So let's take a look here. You guys are in charge. Yeah, what's up? No, it's not a dumb question. What's your question? Totally not a dumb question, but I'm going to just go back to the picture so we can take a look, right? Just so that it's very clear. So the word node means no movement. That's how I remember. Does that make sense? So like this is a node, that's a node, that's a node. Yes. And the nodes would be the cold spots in the microwave. Does that make sense? Whereas the melty spots of gummy bear are going to be where it's an antinode. Yeah, not a dumb question. Thank you for asking. All right, here we go. So the information that I got from Autumn was that the frequency that Josh read was 2,450. Is that right? Or was it 50 or? Oh, okay. That's sad. There you go. Hertz, megahertz. And the distance between melty spots was about right, 5.5 centimeters. Okay, I'm gonna go ahead and let you guys use that information to find the speed of light. Okay, I already gave you the answer kind of, but you want to check it, make sure that I didn't lie to you. All right, there you go. Knock yourselves out. Do some physics. I'm gonna say this real quick too, because again, Not that it's like, not that I want to like discourage you from asking questions, because I totally love it when you ask questions, but just in terms of like finding answers and knowing where to find them. So she's like, what's the equation? And like, I don't know yet. You know, what is it? It is on your equation sheet, but also just, this is kind of a helpful FYI for this equation. So V is equal to F times lambda is the equation. If you're not sure, you can check the units. Units are super easy to check here because this is in meters per second. What's frequency measured in? 1/seconds. And what's lambda measured in? Meters. So do you see how meters per second is meters per second? So you can double check, or if you're not sure if you flipped it, because sometimes that gets kind of goofy. That's just, you know, a way to take a peek. Are you guys done with your math? Almost? Getting close? Did you get the right answer? No? What did you get? Okay. I understand why some, but I'm not completely sure on the other. Did you convert from centimeters to meters? Okay. Convert from centimeters to meters. That's going to fix part of it. So we got to make sure to convert. And I know that no judgment. We're learning together, right? We learn together. That's what we do. That's how we get better. So this thing is really what? So that's 0.055 centimeters. And this is 2.450 times 10 to the, so 6, 7, 8, 9. So now, Eden, I'm not picking on you. I want to learn with you here. What did you get?
1, 3, 4, 7, 5, and then 4 zeros.
Okay, hold on. That was a lot of words that just happened there. Say it again. 1, 4, 2, 3, 4. That's meters per second, right? So 1, 2, 3, 4, 5, 6, 7, 8. So you got 1.3 times 10 to the 8th meters per second. Did anybody else get 1.3 times 10 to the 8th meters per second? Chris, you did too. Okay. Okay, so you're saying, tell me your thought process real quick. What did you say? No. Like, why do you feel good about this answer? So it's got the same like 10 to the 8th thing. That's what you're kind of thinking? Yeah, because it's supposed to be 3 times 10 to the 8th, and you got 1.3 times 10 to the 8th. So it's like ballpark. Okay. Ira's got his hand up though. Yeah. Do you guys understand what he just said? And you can say no. Say no. I'm gonna assume somebody's saying no. Let me make sure I understand what you're saying, Ira. So if we look at one antinode to another antinode, so that's like from here to here, that's this distance. Is that what you're saying? But that's only half of a cycle. Does that make sense? To get a full wavelength, we would need to go from one melty spot, 2 melty spots over, or just multiply this by 2. And Chris, if you do that, so that's like 2.7 times 10 to the 8th, which is also the right order of magnitude, but a whole lot closer to the 3, right? Yeah. I love this demo for so many reasons. One, not the least, which is this one here, right? To recognize that the wavelength is not from one antinode to another, but it's 2 over. I just want to make sure you caught that. Are we doing okay? So this is the right answer, the 2.7 times 10 to the 8th. Thank you to all of you that were volunteering in that way. I've got some other things that I want to hand out to you and talk with you about real quick. So if you leave your whiteboards, you'll leave them for next year. I'm going to send a little pile of these back. Can you send them back, and then TJ maybe can hand them back to me. Oh wait, lies. Hold on. Let me show. What? There are 2 pages. All right, to be less efficient and more accurate.
I have no excuse for that.
Okay, are we good? Good, I'm gonna catch a picture there.
Oh my gosh. Also, the band's getting any answers.
All right. So physicists, some of you voiced concern early on in this unit that rumors have been swirling that this is a hard unit, and it is kind of goofy just because of storms and all of that. So what I did, I have not given this to you for other units, and I will before the AP test, but I felt like today was a good day to provide you with this first set of standards. This is for Unit 6, okay? So this stuff is all directly from College Board, okay? So these are the standards that College Board says that you need to know about for this unit. Now, part of the reason I don't give this to you at the beginning of the unit is because there's a lot of words here, and they're kind of intimidating and scary, I'll be honest. But I would like for you to spend a little time looking through this, okay? And we'll parse this out a little bit tomorrow as well, so that you can identify what things you know, and then figure out before the end of the week and early next week what things you still need to figure out. Does that make sense? Okay. So I want you to hold on to that. I put it on gold paper on purpose. Okay. So take a look through that today and maybe tonight, so that you can come up with some questions if you have them. Okay. The other thing that I want to remind you of before the bell rings is that the AP Classroom Unit 10 progress check number 1, it says Unit 10, because I think I told you that AP says that we're supposed to do this at the very end. So it's their Unit 10, but it's our Unit 6. Okay? I will see you tomorrow. Thanks for a fun day today.